So dear students, now we will discuss about the different type of amplifiers in analog electronic subjects. So what is the power amplifiers? Now we will discuss about the power amplifiers, in which what is the introduction of power amplifier, power and efficiency amplifier classification, basic class A amplifier, transformer coupled class A amplifier. So these are some contents of the power amplifiers. So in introduction, power amplifiers are used to deliver a relatively high amount of power, usually to a low resistance load. And typically load value range from 300 watt for transmission antenna to 8 watt for audio speaker. So although these load values do not cover every possibility, they do illustrate the fact that power amplifiers usually drive low resistance load, and typically output power rating of a power amplifier will be 1 watt or higher, and ideal power amplifier will deliver 100% of the power it draws from the supply to the load. In practice, this can never occur. The reason for this is that the components in the amplifier will all dissipate some of the power that is being, and the amplifier classifications. So we have here class A amplifier, class B amplifier, class C amplifier. So what is the input voltage applied to the class A amplifier, and what is the output? So here in class we applied input voltage, so that is the output voltage, and also in class B and class C. So there is input and output waveforms of the different type of amplifiers. In class A amplifiers, the output waveform is same shape and input waveform plus pi phase shift. So in class A amplifier, the collector current is non-zero 100% of the time. Inefficient, since even with zero input signal, ICQ is non-zero, or collector current at the Q point is non-zero. So transistor dissipates power in the rest or quiescent conditions. The basic operation of amplifier, common emitter voltage divider configuration of RC coupled amplifier given here in this circuit diagram. So this is the RC coupled amplifier common emitter or voltage divider configuration here in this circuit diagram. So typical characteristics curve for class A operation. So this is the graph between collector current versus collector to emitter voltage. So this characteristic curve show the class A operation. And previous in figure, so a sinusoidal input and resulting collector current at the output. In BI characteristics, the current ICQ is usually said to be in the center of the AC load line, and DC and AC analysis discussed in next lectures. So the total DC power PIDC, then an amplifier drop from the power supply. So PIDC will be equal to BCC ICC, and ICC equal to ICQ plus I1. And also ICC is equal to ICQ, where ICQ is large greater than I1. So PIDC will be equal to BCC ICQ. Note that this equation is valid for most amplifier power analysis. We can rewrite for the above equation for the ideal amplifier as PIDC equal to 2VCEQ into ICQ. So this is the PIDC or DC input power. And next, what is the AC output power? So P naught AC equal to IC RMS into V naught RMS, or equal to V naught RMS square upon RL. So this is the AC output power of the class A amplifier. So in these given different characteristics of class A amplifier, here the graph between IC versus BCE, and also a draw DC load line over the VI characteristics. So there is also some Q point, and we have the AC output power P naught AC equal to VCEQ upon under root 2 multiply ICQ upon under root 2. So this will be equal to 1 upon 2 VCEQ into ICQ equal to BPP square upon 8 RL. So efficiency is the PAC upon PDC into 100. So put the value of PAC and PDC. So 1 upon half VCEQ ICQ upon 2 VCQ ICQ into 100. So this will be equal to 25%. So efficiency of class A amplifier is 25%. So there are some limitations, and in this given here the three diagrams. So first is limited by saturation, second limited by cutoff, and third is limited by center Q points. So for example, we calculate the input power PIDC, output power P naught AC, and efficiency eta of the amplifier circuit for an input voltage that result in a base current of 10 milliampere peaks. So with the help of given these data, we can find out some parameters of these examples with the help of different formula. Next one is the transformer coupled class A amplifier. So this is the circuit diagram of transformer coupled class A amplifier, in which the collector is coupled by a transformer, and transformer have the primary winding number of turns N1, and in secondary winding number of turns N2. So the relation between the voltage, current, and number of turns of the primary and secondary winding of the transformer. So N1 upon N2 equal to V1 upon V2, or equal to I2 upon I1. So N1 upon N2 whole square equal to Z1 Z2 equal to Z1 upon RL. So this is the relation between the number of turns and the voltage, currents, and impedance also. So An important characteristics of the transformer is the ability to produce a counter EMF or kick EMF. When an inductor experiences rapid change in supply voltage, it will produce a voltage with a polarity that is opposite to the original voltage polarity. The counter EMF electromagnetic field is caused by the electromagnetic field that surround the inductor. Next, DC operation characteristics. So the DC load line is very close to being a vertical line, indicating that DCEQ will be approximately equal to DCC for all the values of IC. The nearly vertical load line of the transformer coupled amplifier is caused by the extremely low DC resistance of the transformer primary. So voltage VCEQ equal to DCC minus ICQ into RC plus RE. The value of RL is ignored in the DC analysis of the transformer coupled class A amplifier. The reason for this is that transformer provides DC isolation between the primary and secondary winding. Since the load resistance is in the secondary of the transformer, it does not affect the DC analysis of the primary circuit. Next one is AC operating characteristics. So in AC operating characteristics, first determine the maximum possible change in VCE, since VCE cannot change by an amount greater than VCEQ minus 0 volt. So VCE equal to VCQ. Second, determine the corresponding change in IC. So find the value of Z1 for the transformer. Z1 equal to N1 upon N2 whole square Z2 and IC equal to VCE upon Z1. Third one, plot a line that passes through the Q point and the value of IC maximum. So IC maximum equal to ICQ plus IC. Number 4, locate the 2 points where the load line passes through the lines correspond the minimum and maximum value of IB. These 2 points are then used to find the maximum and minimum value of IC and VCE. Next, maximum load power and efficiency. So power supply for the amplifier PS equal to VCC ICC. Maximum peak to peak voltage across the primary of the transformer is approximately equal to the difference between the value of VCE max and VCE minimum. So BPP peak to peak voltage equal to VCE max minus VCE minimum. So maximum possible peak to peak load voltage found by the peak to peak maximum voltage N2 upon N1 into peak to peak voltage. The actual efficiency rating of a transformer coupled class A amplifier will generally be less than 40%. So this is the maximum load power and efficiency of transformer coupled class A amplifier. There are several reasons for the difference between the practical and theoretical efficiency rating for the amplifier. So first is the derivation of the efficiency 50% value assume that VC EQ equal to VCC. In practice, VCEQ will always be same value, that is less the VCC. Second point, the transformer is subject to various power losses. Among these losses are couple loss and hysteresis loss. These transformer power losses are not considered in the derivation of the efficiency 50% value. So these are the some several reasons for the difference between the practical and theoretical efficiency rating for the amplifiers. One of the primary advantage of using the transformer coupled class A amplifier is the increased efficiency over the RC coupled class A amplifier. And another advantage is the fact that the transformer coupled amplifier is easily converted into a type of amplifier that is used extensively in communication, the tuned amplifier. So in a tuned amplifier is a circuit that is designed to have a specific value of power gain over a specific range of frequency. So this is the tuned amplifier circuit. Next amplifier is the class B amplifier. So here the given diagram of class B amplifier explanation. In class B, the transistor is biased just off. The AC signal turn the transistor on. The transistor only conduct when it is turned on by 1/2 of the AC cycle. In order to get a full AC cycle out of a class B amplifier, so you need two transistors. First, an NPN transistor that provide the negative half of the AC cycle, and second, a PNP transistor that provide the positive half cycle. So we need two transistors. Since one part of the circuit pushes the signal high during 1/2 cycle and the other part pulls the signal low during the other half cycle, the circuit is referred to as a push-pull circuit. So circuit referred to as a push-pull circuit or push-pull amplifier. The power supply to the load by an amplifier draw from the power supply. The DC current draw from the source is the average value of the current delivered to the load. So current draw from a single DC supply has the form of a full wave rectified signal, while that draw from two power supply has the form of half wave rectified signal from each supply. So output AC power of class B amplifier, the power is delivered to the load can be calculated using the following equations. So efficiency of the amplifier is given by P naught AC upon Pi DC multiply 100. Note that therefore the efficiency can be re-expressed as eta equal to P naught AC upon Pi DC into 100% or equal to VL P square upon 2RL divided by VCC into 2 upon pi IP into 100. So this will be equal to pi upon 4 into VL P upon VCC into 100. So efficiency can be re-expressed as by this formula. So maximum efficiency can be obtained if VLP equal to VCC. So in that case, the value of this maximum efficiency will be pi upon 4 into 100, that will be 78.5%. So maximum efficiency of class B amplifier is 78.5%. The power dissipated by the output transistor as heat is given by P2Q equal to PIDC minus P naught AC. So the power in each transistor is given by PQ equal to P2Q upon 2. So here are examples for a class B amplifier providing a 20 volt peak signal to 16 ohm speaker and power supply of VCC is 30 volt. Determine the input power, output power, and the efficiency. So we can find out the these input power, output power, and efficiency by the given formula. So next, the maximum power dissipated by the two transistors occur when the output voltage across the load is given by BL P equal to 0.636 VCC or equal to 2 by pi into VCC. The maximum power dissipation is given by 2 VCC square upon pi square RL. Next one is the class C amplifier. So this is the circuit diagram of class C amplifier and relation between the input power and output power of class C amplifiers given here in this second diagram. So in class C operation, IC collector current should be flowing less than half cycle. Q point is at below cutoff of the operating range. So here base resistance and BBB voltage across the base DC provide a required below cutoff IBQ for a class C operation. Q point is below the cutoff of the operating range IBQ. So this is the class C operation. Here also a DC power from VCC is converted into AC input power. So this is tuned class C RF power amplifier or radio frequency amplifiers that is given in this circuit diagram. And next one is the amplifier efficiency. So an important consideration in the design of power amplifier is efficiency. So efficiency equal to power dissipated in the load divided by power observed from the supply. So this is the efficiency of amplifier, and efficiency determines the power dissipated in the amplifier itself. So power dissipation is important because it determines the amount of waste heat produced. So excess heat may require heat sink, cooling fans, etc. So efficiency rating, the maximum theoretical efficiency rating of class A, class B, and class C amplifier are. So class A amplifier have the maximum theoretical efficiency is 25%, and class B have the maximum theoretical efficiency is 78.5%, and class C have the maximum theoretical efficiency 99%. So Next one is the push-pull amplifiers. So what is the push-pull amplifiers? In analog push-pull power amplifiers, the two output devices, transistors, tube, FET, or set of device operate in anti-phase or 180-degree apart. The two anti-phase output are connected to the load in a way that causes the signal output to be added. What distortion components due to non-linearity in the output devices with the subtracted from each other if the non-linearity of both output device is similar. Distortion is much reduced symmetrical push-pull circuits. So next one is the class B amplifier push-pull operation. So in class B amplifier push-pull operation, this is the circuit diagram given here for the class B push-pull amplifier. Here there are two transistors Q1 and Q2 and also a center tap transformer between it, the input and output also. And so there is total four parts. First part is the phase splitting input transformer. Second one is the push-pull circuit connections. And third one is the push-pull output transformer. And last one is the load. So during the positive half cycle of the AC input, transistor Q1, that is the NPN, is conducting, and transistor Q2, that is the PNP, is off. So in this circuit diagram, first positive cycle transistor Q1 is on and transistor Q2 off. What during the negative half cycle of the AC input, transistor Q2 PNP is conducting and Q1, that is NPN, is off. So each transistor produces one half of an AC cycle. The transformer combines the two outputs to form a full AC cycle. This circuit is less commonly used in modern circuits. So this is the applications of class B push-pull amplifier. And the input signal to the amplifier could be a single signal. The circuit then providing two different output stages, each operating for one half the cycle. If the input is in the form of two opposite polarity signals, two similar stages could be used, each operating on the alternative cycle because of the input signals. One means of obtaining polarity or phase inversion is using a transformer. The transformer coupled amplifier having been very popular for a long time. Opposite polarity input can easily be obtained using an op-amp having two opposite outputs. So that is given in these circuit diagrams. So the circuit uses center tap input transformer to produce opposite polarity signal to the two transistor input and an output transformer to drive the load in a push-pull mode of operation described next. During the first half cycle of operation, transistor Q1 is driven into conduction, whereas transistor Q2 is driven off. The current through the transformer result in the first half cycle of signal to the load, And during the second half cycle of the input signal, transistor Q2 conduct, whereas Q1 stay off. The current I2 through the transformer resulting in the second half cycle to the load, the overall signal developed across the load when varies over the full cycle of signal operation. So that is the transformer coupled push-pull amplifier circuits. Next one is the complementary symmetry circuit push-pull amplifier. So in this push-pull amplifier using complementary transistors NPN and PNP, it is possible to obtain a full cycle output across a load using half cycles of operation from each transistor as shown in figure 5. As shown in figure in below. So in this figure, that is the complementary symmetry circuits of push-pull amplifier. Next one, amplifier distortions. So a pure sinusoidal signal has a single frequency at which the voltage vary positive and negative by equal amounts. Any signal vary over a less than the full 360 cycle considered to have a distortion. An ideal amplifier is capable of amplifying a pure sinusoidal signal to provide a larger version, the resulting waveform being a pure single frequency sinusoidal signal. When a distortion occurs, the output will not be an exact duplicate except for magnitude of the input signal. So there are some harmonics. So what is the harmonics? Harmonics are integer multiple of a fundamental frequency. If the fundamental frequency is 5 kilohertz, so first harmonic is 5 into 1 kilohertz, and second harmonic 2 into 5 kilohertz, and third harmonic 3 into 5 kilohertz, and fourth 4 into 5 kilohertz, and etc. So note that the first and third harmonic are called odd harmonics. First and third are odd harmonics, and the second and fourth called even harmonics. So these are the fundamental frequency harmonics. Next one is crossover distortion. So in this diagram, the crossover distortion shown here. So if the transistor Q1 and Q2 do not turn on and off at exact the same time, then there is a gap in the output voltage. So given here, that is the crossover distortion. And in harmonic distortion, according to Fourier analysis, if a signal is not purely sinusoidal, then it contains harmonics. So in given here different waveforms, so in last waveform there is some harmonic distortions. So there are some multi-choice questions for this topics. The use of amplifier in a circuit is to for input signals. Option A, provide a phase shift. Option B, provide a strength. Option C, provide frequency enhancement. Option D, make circuit compatible. So here correct answer is option B. The use of amplifier in a circuit is to provide a strength for a input signal, because in amplifier the input signal is applied to any amplifier. The output of any amplifier will be increase the strength of the signal. So that is the use of amplifier, to provide a strength to the input signals. In next questions, unwanted characteristics of amplifier output apart from the desired output is collectively termed as a inefficiency, damage, fault, distortion. So correct answer here is option D. Unwanted characteristics of amplifier output apart from the desired output is collectively termed as a distortion. So correct answer is option D. In next questions, unit of power rating of a transistor is expressed in unit of power rating. Option A, watt. Option B, kilowatt hour. Option C, watt per second. Option D, watt hour. So unit of power rating of a transistor is expressed in watt. So correct answer is the option A. In next questions, which device was used for the amplification of audio signal before the invention of power amplifier? So before invention the power amplifier, which device was used for the amplification? Basically, amplification means increase the strength of the any signals to a low level to high level. So option A, diode. Option B, op-amp, that is the operational amplifier. Option C, that is the vacuum tubes. And option D, silicon control rectifier. So here correct option is vacuum tubes. Vacuum tubes, before the invention of power amplifier, we use these tubes for the amplification purpose. And here diode is used as a rectification purpose, or rectification means increase, convert the AC supply to the DC supply. And op-amp is the operational amplifier, that is the also a amplified device. In the operational amplifier, we do the different calculation, addition, summation, and integration, differentiation, etc. And SCR, that is the silicon control rectifiers, that is also used for rectification in high power conversion. So here correct option is option C, vacuum tubes. Next question, power amplifiers directly amplify option A, voltage of a signal, option B, current of the signal, option C, power of the signal, option D, all of the mentioned. So basically power amplifiers are different types, class A, class B, class C, class AB. So all these power amplifiers, these are amplifies the voltage of a signal, or we can say the increase the strength of the voltage low level to high level, and also increase the current strength of the signal, and also increase the power of the signals. So here the power amplifier directly amplify all the mentions here. So correct answer is D, because power amplifier amplify the voltage, current as well as power also. In next questions, input stage of power amplifier is called first output, beginning stage, front end, normal stage, input stage of the power amplifier. So correct answer is front end. So this is the input stage of power amplifier, because in power amplifiers there are different stages. So that is the RC coupled common emitter power amplifier. So here given there are different stages. So in this diagram there is a input AC signal and a capacitor also across the base of the transistor. So here transistor is the NPN, and also here there is a two resistance, that is the R1 and R2, that is the biasing resistance for the power amplifier, and they provide the biasing for this power amplifier, and there also a resistance across the emitter terminal, that is the RE, and also a capacitor across the this emitter terminal, and this capacitor used as a bypass capacitor. So for preventing the feedback concept, we use here the bypass capacitor, and also there is a collector resistance across the collector terminal, and a DC voltage supply here, that is the VCC, that is applied across the transistor collector terminal, and a output capacitor is also connected across the collector terminal, and a load resistance, and we measure the output power across the load here. So RL is the load. So in power amplifier, a speaker we have as a load. So this is the different stage of power amplifiers, and that is the example a common ammeter voltage divider or a RC coupled amplifiers. Thank you.